Okay, let's talk about decibels. Decibels are used to compare two things. They're used for ratios, and they have a logarithmic scale. So when you have things that differ from each other by a lot quickly, then it's useful to use a logarithmic scale. And so we use logarithmic scales for things like sound intensity, and earthquake magnitudes are also logarithmic in nature. And a decibel is really just a ratio to some fixed value. But if we don't have, some fixed value that we're planning to use, you can set your fixed value to be 1 of whatever your unit happens to be. So when we do Bode plots, we're going to use these logarithmic ratios, and what they will include, whenever you're using decibels, you'll have a scale factor for whatever kind of units you're looking at. And so for Bode plots, when we're doing power ratios, when we're looking at the power, our scale factor is 10. So if I want to convert a power ratio to decibels, then I'm going to take this 6e to the third, and my gain in decibels is going to be 10 times the log of 6e to the third, and then my reference is just 1. Now, I'm going to show you some things to remind you about the properties of logarithms that you probably have forgotten since high school, but just to remind you, because they are important to know, because this is how gains combine with each other. Well, I forgot my 10. So first of all, 10 is a power ratio. It tells us it's a power ratio, so I have a 10. But the log of a product is the same as the sum of the logs. So this is the same as 10 times the log of 6 plus, and exponents can come down in front of the log, 3 log of e. And if I do that, that's 10 log 6 plus 30 log e. And that's common log, which is log base 10. And I get 20.81 decibels. Okay, now if I were to do, I'll skip to, well, I'll do B. So I have B would be the gain in decibels is 10 log 2.3 times 10 to the third plus 60, which, now I can't separate out the plus. It's only when it's multiplied that I can do that, but when it's added, I can't. So I just need to take 2300 plus 60, which is 2360, and then 10 times the log of 2360 is 33.73. That's different than in part C, where I have, it would be 10 times, the B is capitalized, 10 times the log of 24 times 3 times 10 to the 7th. Well, this is all multiplied, so I could make this, if I wanted to, 10 times the log of 24 times the log of 3 times the log of 10 to the 7th. So it's 10 times the log of 24. Oops, this is plus the log of 3. Now, because this is common log base 10, the log of 10 to the 7th is just 7. And then I can figure out what this is. 10 log 24 is 13.8, and 10 log 3 is 10 log 3. It's something, don't know what, plus 7, and so then that is 20.8 plus 10 log 3, at which point I do have to get out the calculator, and it is 85.57 decibels. And then the last one here, I just want to show you a division. So I have 10 times the log of 4 over 5 times 10 to the third. So the log of a quotient is the same as the difference of the log. So this is 10 times the log of 4 minus the log of 5 times 10 to the third, which is 10 times the log of 4 minus the log of 5 minus 3. And then that is just what it is. Negative 30.97. Okay, now when that's for power, when you're doing voltage or current, you use 20 instead of 10. It's just a different scale factor, and it's just by definition. So if I wanted to get the gain, say, but this is going backwards. So if I had the same problem here, but it wasn't power ratios, but it was voltage ratios or current ratios, then I would use 20 instead of 10. But here I'm going the other direction. So this time I've got the decibels, and I want to convert them to voltage ratios. And so I need to remember that for voltage I use 20, and the way I do this is that my voltage ratio is going to be, for the first one, is going to be 10, and then raised to this number 46 over my scale factor, which was 20. So this is 10 to the 2.3, and 10 to the 2.3 is it really 199.5? I don't know if I believe that. Let me check that. Huh. Notice the 0.3. Oh, it did. I was getting confused. Okay, yeah. So 199.5 for part A, and then for part B, let's just go on to D. So D, and then the 20 came in here from the scale factor because we're doing voltage. So for part D, the voltage ratio would be 10, and that 10 is the same for all of them. It comes from the fact that it's a common log, to the negative 66 over 20, which is 10 to the negative 3.3, and 10 to the negative 3.3 is 5.0 times 10 to the negative 4.